between the endless night, where ancient stars whisper their billion-year secrets. We touch a question as old as the cosmos itself. Where does it end? The Edge of the Universe Explained invites you into a journey where science becomes soft as breath, and space flows like a gentle river carrying us through stillness. Here, every photon is a messenger, every galaxy a living soul, every discovery a doorway opening toward awe. It is a place where we feel small yet overwhelmingly magnificent at the same time, as if drifting peacefully through the universe's quiet heart. If you love silence, if you long to wander beneath the deep sky, press like and subscribe so we may continue listening to the universe together. So then, does the universe have an edge? Since the earliest nights when humanity first lifted its eyes to the dark sky, we have been haunted by a question so simple yet so immense that it shakes the foundations of our understanding. Does the universe have an edge? An ultimate boundary where existence itself comes to a stop. This question appears innocent, almost childlike. Yet it leads us into the deepest waters of cosmology, philosophy, and the limits of language. As the physicist Richard Feynman once said, "I think nature's imagination is so much greater than man's. She's never going to let us relax." And truly, this question never lets us relax. When we ask if the universe has a rim, we imagine a cosmic wall, a final frontier, some luminous or shadowed barrier floating at the farthest reach of space. We imagine reaching it in a starship, pressing a hand against it, and wondering what lies beyond. Such imagery is beautiful, poetic, deeply human. Yet physics warns us that the charm of the question may conceal a faulty premise. Stephen Hawking once remarked, "Asking what lies outside the universe is like asking what lies south of the South Pole." Still, the mind resists. Because on Earth, everything has an edge, a shoreline, a limit. We are shaped by borders, by walls, by the sense that all things begin and end somewhere. So we project this intuition outward, onto the grandest canvas we know, the cosmos itself. Suppose for a moment the universe did have a wall, some kind of boundary where space abruptly halts. What would it look like? A shimmering veil, a silent, infinite plane, a region where physics collapses. And if we could stand before it, would the other side contain empty space, or the absence of space altogether? Here the mind begins to bend. Because the absence of space is not something we can picture. Space is the stage upon which our thoughts operate. Even our imagination requires it. Asking what lies beyond space might simply be a misuse of our vocabulary. Einstein hinted at this when he said, "The distinction between past, present, and future is only a stubbornly persistent illusion." His point applies here too. Many distinctions we cling to may be illusions of our limited perspective. Modern cosmology suggests that space might be finite yet unbounded, like the surface of a sphere. The surface of Earth is finite, yet you can walk forever and never fall off an edge. In the same way, the universe might loop back on itself in dimensions our senses cannot grasp. If this is so, traveling in one direction long enough could theoretically bring us back to our starting point. A breathtaking idea that transforms the universe from a container into a kind of cosmic shape. This idea also explains why the question, what is outside the universe, may be meaningless. Just as there is no outside to the surface of Earth in 2 dimensions. There is only the surface, and the concept of outside belongs to a higher dimension not accessible to a 2-dimensional being. As Carl Sagan beautifully put it, we live in a universe exquisitely tuned for life, but we struggle to tune our minds to the universe. And yet, the human heart persists in its longing for answers. We ask because we are creatures of metaphor. We understand by analogy. So when cosmologists say the universe may be finite but unbounded, they do not mean there is a literal sphere floating in some higher space. They mean simply that the geometry of spacetime can close in on itself without needing a physical barrier. But if the universe has no edge, why do we instinctively feel that it must? The answer lies in the way the brain evolved, built for survival on a planet of discrete objects and sharp boundaries. Our ancestors survived by recognizing cliffs, rivers, the edges of forests. To them, edges meant danger, safety, territory. And so we inherited a mind optimized for edges, not for smooth, infinite geometries of spacetime. Physics offers a gentle correction to this inheritance, reminding us that our intuition is not the measure of reality. Many truths of the cosmos exist far outside the scope of what evolution needed us to understand. As Neil deGrasse Tyson says, the universe is under no obligation to make sense to you. The deeper lesson here is humility. We live inside a vast structure that does not owe us simplicity. Our minds are young, the cosmos ancient. And yet, our ability to ask these questions is itself astonishing. A species that evolved on a small blue planet, around an ordinary star, in a quiet corner of a galaxy, has dared to challenge the boundaries of existence itself. For me, reflecting on the edge of the universe is more than scientific curiosity. It is a meditation on perspective, a reminder that our assumptions are often shadows of our limited view. In asking where the universe ends, we confront the limits of language, the boundaries of intuition, and the profound mystery of existence. We discover that the real edge may not lie at the rim of the cosmos, but at the edge of our understanding, and that boundary is always moving, always expanding, much like the universe itself. Every insight pushes the horizon a little further. Every discovery widens the circle of what is knowable. And in this expansion, we find both our humility and our glory. The concept of the edge of the universe is, therefore, not a physical location, but a mirror held up to the human mind. It shows us where our thoughts can no longer walk, where our analogies break, and where wonder begins. And perhaps this is the true gift of cosmology. It teaches us that not all questions must have answers. Some exist simply to widen the soul. In contemplating a universe without walls, we learn to live with open curiosity, to embrace the infinite, and to understand that our journey is not toward a distant edge but inward, toward deeper clarity. And so we return to the question, gentle yet profound: does the universe have an edge? And we discover that the true answer is not found at the borders of space, but at the expanding frontier of the human mind. Space and time, those two quiet companions that cradle every moment of our existence, are often imagined as separate realms, one for where things are, and one for when things happen. Yet, modern physics whispers a different truth, a more intricate, more poetic fabric beneath reality. A single unified tapestry called spacetime, a living geometry that bends under the weight of matter and energy. Einstein once said that time and space are modes by which we think, not conditions in which we live. And in that sentence lies the first doorway into the strangeness of the universe we inhabit. Space-time can curve because it is not a rigid stage. It is an active participant. The presence of mass gently presses into this fabric, making valleys and contours in a dimension we cannot touch directly. In the words of John Wheeler, matter tells space-time how to curve, and space-time tells matter how to move. This is not metaphor. It is the most accurate description humanity possesses of gravity's true nature. When a planet orbits a star, it is not being pulled by an invisible force. It is simply following the straightest possible line across a curved landscape. And when we understand that, we begin to see that our universe is not a box, but a shape. This idea prepares us for another revelation, one that strains the imagination yet remains perfectly consistent with mathematical truth. A three-dimensional universe like ours can behave as though it is the surface of a four-dimensional hypersphere. Not on the surface, in any physical sense, but in the way distances connect, in the way directions wrap, in the way straight lines eventually meet again. Just as a two-dimensional being walking on Earth's surface would never find an edge, we too might wander the cosmos forever without encountering a wall. Stephen Hawking once suggested that the universe is finite but has no boundary. And though the phrase appears paradoxical, it provides one of the most intuitive gateways into this vast and subtle geometry. We are not trapped in a sphere, but we may be living on a curved manifold whose full shape extends beyond ordinary perception. This perspective dissolves another deeply human assumption, the idea that the universe must have a center. We look to the stars the way ancient navigators looked to the sea, expecting a point of origin, a cosmic birthplace. But in a curved space-time where expansion happens everywhere at once, no place can claim that title. Every galaxy sees all others rushing away. Every observer stands at the apparent midpoint. The observable universe becomes a personal bubble, not a universal blueprint. What we call the center is simply where we happen to be, and every other civilization would say the same. As Alan Guth once remarked, the universe is not expanding into anything. It is simply getting bigger. And this truth removes the need for a central anchor. If the cosmos lacks an edge and has no center, then what happens if we travel in one direction forever? In a curved universe, The answer is startling. We may return to where we started, not because we turned, but because space itself loops. This is the same phenomenon that would confound a two-dimensional creature walking across Earth. It believes itself on an infinite plane, yet one day it arrives home from the opposite side. Our universe may be the three-dimensional analog, a place where straight lines are only straight within a higher dimensional curvature. It feels abstract, but the mathematics is precise. And it is this precision that allowed Einstein's theory to predict starlight bending, black holes forming, and gravitational waves rippling through existence. The balloon model brings these ideas down to Earth. Imagine galaxies as dots on a rubber surface, and the balloon slowly inflating. None of the dots move across the surface, yet all drift apart. The expansion occurs everywhere uniformly, without a center on the surface itself. This simple image captures the behavior of our universe's expansion with remarkable clarity. It reveals why distant galaxies appear to flee faster, why no direction is privileged, why the observable universe forms a sphere around each observer, and why asking what is outside the universe becomes as meaningless as asking what lies beyond the edge of a balloon's surface. As a scientist, what strikes me most is not just the logic, but the humility these ideas demand. The more we understand spacetime, the more we sense our own limitations. The universe refuses to be boxed into human intuition, and every discovery feels like a gentle correction from a teacher far older than our species. We learn that boundaries we cling to are often inventions of the mind, not features of reality. And from this comes a lesson worth carrying into daily life, that the world is rarely as small or as closed as it seems. Perspective can curve, assumptions can stretch, and journeys that appear linear may be loops that guide us home wiser than before. Carl Sagan once wrote that understanding is a kind of ecstasy, and nowhere is that truer than in the study of space-time. For it is here that science becomes poetry, where equations reveal landscapes more beautiful than any myth. Here, in the quiet curvature of the universe, we find a cosmos that is not empty, but alive. A cosmos that invites us not merely to observe, but to belong. And as we navigate its mysteries, we discover that every question we ask about the universe is also a question about ourselves, the shape of our curiosity, the limits of our understanding, and the courage it takes to walk straight into the unknown. In the end, spacetime's curvature is not just a physical property. It is a metaphor for learning. The more mass we gather in the form of knowledge, the more richly our internal universe bends, and the more gracefully our perspective moves along its contours. Perhaps that is the quiet truth behind all cosmology, that by studying the universe, we reshape the space within ourselves. And in that inner expansion, we find that wonder, like space-time, is endless. In the quiet vastness of the cosmos, we often imagine galaxies as ships thrusting through a dark ocean, propelled by some invisible engine. But the truth whispered by modern cosmology is softer, more subtle, and far more astonishing. It is not the galaxies that rush away from us. It is the ocean itself that stretches beneath them. Space is not a silent stage but an active participant, a living fabric capable of swelling, flowing, and reshaping the distances between every cluster of stars. Einstein once remarked that space is not merely a backdrop for events, but something with physical qualities of its own. And it is precisely this insight that unlocks the mystery of cosmic expansion. When we observe distant galaxies drifting away, their light stretched into deeper red, we might imagine them accelerating outward like sparks flying from an explosion. Yet no explosion behaves this way. In an explosion, matter spreads from a center, and observers located elsewhere would measure different patterns of motion. Instead, every observer in every galaxy sees the same thing. All other galaxies receding from them in direct proportion to distance. This universal symmetry led Edwin Hubble to propose that the expansion comes not from matter's motion but from space itself, unfurling like a cosmic tapestry. If space expands, then no center is required. For how can a stretching fabric have a privileged point? Stephen Hawking once said, "Asking for the center of the Big Bang is like asking for the edge of Earth's surface." The question dissolves because the geometry itself forbids an answer. The Big Bang was not an outward explosion in pre-existing emptiness. It was the sudden emergence of space itself. Every point, everywhere, igniting at once. And in that moment, the distances between all future galaxies began to grow, not because the galaxies were fleeing, but because the very fabric between them was stretching. This leads naturally to the haunting question: if space is expanding, what is it expanding into? The answer feels counterintuitive because our minds are shaped by earthly experience. A balloon expands into the surrounding air. A wave ripples across a lake. But the universe is not a balloon suspended in a larger room, nor a ripple moving across some external backdrop. Space is everything that exists. And expansion is not movement into a larger void, but an internal increase in distances within the universe itself. As cosmologist Sean Carroll beautifully phrased it, space does not expand into anything. It simply becomes more of itself. This swelling of space also explains how galaxies can appear to recede faster than light without violating relativity. No object can travel through space faster than light. But relativity places no limit on how fast space itself can expand. A distant galaxy may remain perfectly still in its own local frame. Yet the space between us grows so rapidly that its light never reaches our telescopes. Alan Guth, the father of inflation theory, once noted that the speed limit applies only to motion through space, not to the stretching of space itself. This single distinction reshapes our understanding of what is possible. As we follow these ideas, their emotional weight becomes impossible to ignore. We suddenly find ourselves in a universe with no center, no boundary, no outside. A realm where every observer stands at the heart of their own expanding sphere of reality. The galaxies drifting away are not abandoning us. They are participating in the slow, graceful unfolding of space-time itself. And in that unfolding, we glimpse a deeper truth: that the cosmos grows not because something pushes it, but because expansion is woven into its very nature. Personally, I find this vision humbling and strangely comforting. The universe is not a violent explosion, but a patient blooming, a quiet widening that continues even now in the silent dark between galaxies. It teaches us that movement is not always force, that change need not be chaotic, and that the greatest transformations can happen without sound or shock. There is a lesson hidden here, a reminder that growth in our own lives often works the same way, gently, invisibly, from the inside out. And as we contemplate this ever-expanding cosmos, we discover a deeper connection to the question that set all these ideas in motion. If space stretches without center or boundary, if galaxies drift apart because the universe itself is breathing, then what does it truly mean to ask where it all leads? And what mysteries still wait for us in a universe where even the farthest lights are being carried beyond our reach? Since the first human eyes looked upward into the night, we have lived with a quiet astonishment. The recognition that the deeper we gaze into the cosmos, the further backward we drift along the river of time. Light is our messenger, our single thread connecting present experience with ancient events. And every photograph captured by a telescope is not a portrait of what is happening now, but a preserved memory of what once was. As the astronomer Arthur Eddington once remarked, we are not looking at the universe as it is, but as it was. This is why looking far away is the same as looking into the past. A star 10 light-years distant shines into our eyes with photons that began traveling a decade ago. A decade during which empires rose and fell. Storms struck our world, and children were born. By the time that light touches our retinas, the star may have changed. Its surface may have shifted, or in rare cosmic tragedies, it may no longer exist. The past is always arriving, softly, endlessly, and with a patience impossible for living creatures bound by heartbeat and breath. Consider the Andromeda Galaxy, our vast spiraling neighbor, sailing through space like an ancient ship carved from starlight. When we see it glowing faintly in telescopes, we are not seeing Andromeda as it is today, but as it was 2.5 million years ago. Its light left long before any human species walked upright, before tools, before fire, before the first stories were shaped by trembling hands around a campfire. Carl Sagan expressed this quiet wonder by saying, "To look at Andromeda is to look across an ocean of space and into an ocean of time." This delay is not a flaw. It is a fundamental truth of reality. Light has a finite speed, the cosmic limit set by nature itself. Because of that limit, the farther we peer, the older the message becomes. And the universe, with its grand age of 13.8 billion years, imposes a boundary on what we are capable of seeing. We cannot witness events older than the cosmos itself, for there is no light older than the universe to deliver those stories. Astronomers call this principle look-back time, the measure of how far backward an observation reaches. If we observe a galaxy 10 billion light-years away, we are witnessing a moment 10 billion years in the past, when the universe was young, hot, and roaring with newborn stars. Look-back time transforms every telescope into a time machine, a device that lets us peel back the layers of creation one photon at a time. Yet there is an even grander question, one that leads us to the heart of the observable universe. If the cosmos is 13.8 billion years old, why is our observable horizon nearly 46.5 billion light-years away? The answer lies not in the speed of light, but in the growth of space itself. As the universe expands, the fabric of spacetime stretches, carrying ancient photons on an ever-lengthening road. A galaxy that emitted its light 13.8 billion years ago is no longer where it once was, the space between us having swollen with cosmic expansion. When that earliest light finally reaches us, the galaxy that sent it has drifted far beyond 13.8 billion light-years, out to a staggering 46.5 billion. Thus, our observable universe is not simply defined by age, but by the ongoing stretching of reality itself. The cosmologist Brian Greene described this beautifully. The universe is not expanding into anything. It is simply creating more of itself. This expanding horizon forms a sphere centered around each observer, a personal bubble of visibility, a delicate shell separating the knowable from the unreachable. Beyond that shell exist galaxies whose light will never reach us, carried forever away by the swelling tide of space-time. As Stephen Hawking once said, the universe is not only stranger than we imagine, it is stranger than we can imagine. And nothing demonstrates that strangeness more clearly than the idea that most of the universe is permanently hidden from us. When we face this truth, something shifts inwardly. We begin to understand that every image we see of the cosmos is a preserved memory, a fossil of light. The night sky becomes not a ceiling, but an archive, a library of ancient stories written in photons. And in that recognition, we find both humility and wonder. As a scientist, I am continually moved by the paradox that our limitations become our greatest teachers. The fact that we cannot see the entire universe forces us to appreciate the fragile miracle of what we can see. The fact that we observe the past rather than the present reminds us that time is not an enemy, but a companion. And the truth that light takes ages to arrive teaches patience, teaching us that understanding often comes slowly, steadily, like dawn moving across a quiet horizon. The lesson we take from look-back time is not simply scientific, it is human. We too are traveling through a universe whose messages arrive late. We too see the past in the people around us, shaped by memories, choices, and echoes of earlier chapters. And just as we cannot see beyond the cosmic horizon, we cannot yet see our own future. But we can move toward it with curiosity, clarity, and courage. Ultimately, the idea that looking far is looking back reminds us that the universe is a storyteller, and we are fortunate enough to be listening. In every distant galaxy, in every faint red-shifted glimmer, a piece of cosmic history is delivered to our fragile world, inviting us to understand where we come from. In that sense, the Big Bang explained is not only the story of creation, it is the story of us. And every photon that reaches our eyes is a reminder that even across unimaginable distances, the universe still reaches out to touch us. Since the earliest days of modern cosmology, scientists have stood in awe before a quiet contradiction shimmering across the sky. The cosmic microwave background, a faint fossil glow, looks almost perfectly identical in opposite directions, even though those regions have never shared a single whisper of contact. Stephen Hawking once remarked that the universe is not only stranger than we imagine, it is stranger than we can imagine. And nowhere is this strangeness more evident than in the smooth uniformity of that ancient light. A uniformity so precise that it challenges our most basic sense of causality. Imagine two patches of sky separated today by 90 billion light-years. Their photons taking nearly the entire age of the universe to reach us. And yet, they match in temperature to 1 part in 100,000. Alan Guth, father of inflation theory, once said that this near-perfect agreement cries out for an explanation, and inflation offers a graceful one. Before the universe expanded into its great tapestry, all regions we now see were once compressed into a space smaller than a proton. They were in intimate contact, exchanging heat, smoothing themselves into equilibrium. Then, in an unimaginably small fraction of a second, the fabric of reality ballooned outward faster than any force could counter. This inflationary breath stretched that tiny uniform patch into the vast cosmic sphere we observe today. And from here, another question rises like a tide beneath the starlight. Why is the universe so enormous? Why does it contain such vast gulfs that no light will ever cross? Why is creation so extravagant? The inflationary moment did more than smooth space. It inflated the scale of the cosmos to a size far beyond what a slow, gentle expansion could ever produce. Physicist Max Tegmark notes that if inflation happened even slightly differently, our universe might have been a tiny, closed bubble, collapsing upon itself before stars could ignite. But instead, it was granted enormous room to breathe, room for galaxies to form, for stars to live and die, for planets to rise, and eventually for minds like ours to question it all. Yet even this vastness is not the universe's final surprise. For when we turn our gaze to the most distant galaxies, we see them racing away faster than the speed of light. At first, it seems a violation of Einstein's cosmic rule, a breaking of the speed limit written into the bones of physics. But the galaxies themselves are not speeding through space. Rather, space itself is widening between us and them. Like dots painted on the surface of a balloon, they drift apart because the rubber beneath them stretches, not because the dots move. This expansion can outrun even light, and yet no physical law is broken. What it means, however, is something profoundly humbling. There are galaxies we see today whose future light will never reach us. They are carried away on the accelerating tide of space-time itself. Their stories, their collisions, their futures are forever severed from our cosmic narrative. This is what astrophysicists call the horizon of causal disconnection, a boundary not of matter but of meaning. The source of this relentless expansion appears to be something even more mysterious, something the scientific community calls dark energy. It is a presence woven into the vacuum, a quiet pressure that pushes galaxies apart with increasing strength. Nobel laureate Adam Rees once said that dark energy is the most embarrassing gap in our understanding of the cosmos, because it behaves like nothing we have ever measured. It is invisible, untouchable, yet it dictates the fate of everything that exists. As the centuries pass, dark energy will continue to widen the universe until the most distant galaxies slip beyond visibility. Future astronomers may find themselves alone in a darkening sky, surrounded only by the remnants of their own local group. The vast cosmic web, which today glitters across billions of light-years, may one day fade entirely from sight, leaving behind a lonely island of stars, unaware that a grand ocean ever existed beyond their shores. This prospect presses on the heart like a soft weight, urging us to reflect on our own place within the cosmic story. The mysteries we explore are not simply lines in a textbook. They are reminders that our moment in time is brief, that our window onto the universe is precious. Neil deGrasse Tyson once reflected that we are part of the universe trying to make sense of itself, and that awareness is a form of cosmic privilege. Thinking about the perfect symmetry of the CMB, the vastness of cosmic space, the breathtaking recession of faraway galaxies, and the unknowable force of dark energy leads us into a deeper understanding, not only of physics, but of perspective. The universe is immense precisely because it is ancient, complex, and governed by laws we are only beginning to touch. Its mysteries are not flaws but invitations, asking us to look again, to wonder more deeply, to accept that awe is a form of knowledge. And beyond the data, beyond the equations, lies a quieter truth. Everything we observe, everything we question, everything we try to understand, reflects the same impulse that guided our ancestors beneath the first night skies. Curiosity, that fragile flame, is our bridge to the infinite. It keeps us from shrinking before the darkness, reminding us that learning is not an escape from our smallness, but a celebration of it. Perhaps that is the lesson hidden in the CMB's perfect smoothness, in the universe's swelling immensity, and in the impossible flight of distant galaxies. That understanding is always partial, that mystery is not the enemy of knowledge, and that the universe does not owe us simplicity. What it offers instead is wonder, and that may be the most valuable force of all. As we drift through this cosmic meditation, we realize that our questions reveal more about us than about the stars. Each mystery we touch is a reminder of our desire to reach beyond ourselves, to join the universe in its quiet unfolding. And that journey, like the expanding sky itself, has no true boundary. If the cosmos teaches us anything, it is that curiosity is as vast as space and far more luminous. Inflation is one of those ideas that seems at first like a mathematical trick, a clever adjustment to make the early universe behave more neatly. Yet the deeper you go into it, the more it reveals itself as a breathtaking turning point in our understanding of the shape of the universe. A moment when physics discovered that creation itself may have unfolded in a flash so violent, so impossibly fast, that every trace of its fury was swept smooth like wind erasing footprints in desert sand. Alan Guth, the father of inflation theory, once said, "Inflation is the miracle that makes the unlikely inevitable." And the more we study this idea, the more that sentence feels like a key turning inside a lock. To understand inflation, Imagine rewinding the universe to a moment far earlier than we can directly see. Before the cosmic microwave background, before atoms, before even the familiar geometry of space took shape. In that first sliver of time, time itself had barely begun. The universe was smaller than a proton, a chaotic sea of quantum energy, where fluctuations were not tiny whispers but roaring storms of probability. Inflation proposes that in this instant, some field of energy, perhaps the so-called inflaton field, fell into an unstable state. A delicate imbalance triggered a surge, and the universe expanded at least a trillion times in a fraction of a second. As physicist André Linde put it, the universe was born not once, but many times, everywhere, forming a self-reproducing cosmos. This furious expansion does something remarkable. It explains why the universe looks the same in every direction. Without inflation, two regions of space on opposite sides of the sky should never have communicated, never shared heat, never synchronized their temperature. And yet the cosmic microwave background shows a universe astonishingly uniform, differing in temperature by only 1 part in 100,000. Inflation smooths the puzzle elegantly. It tells us that all the regions we now see were once close together, compressed inside an unimaginably tiny patch. They reached thermal equilibrium. Then inflation stretched them beyond each other's horizons. What looks like impossible coordination becomes the natural consequence of a universe that expanded too quickly for its own history to remain visible. But inflation does more than smooth the cosmos. It shapes it. If you inflate a balloon, every wrinkle flattens, every crease softens. Inflation applies that same logic to the shape of the universe, taking whatever curvature the early universe once had and stretching it outward until it becomes almost perfectly flat. Observations today confirm this with stunning precision. The geometry of space is flat within 0.5%. Stephen Hawking once remarked, "Inflation predicts the universe should be flat." And so far, the observations agree. This is not coincidence. It is the echo of that primordial stretching. Yet while inflation erases large-scale irregularities, it amplifies the tiny ones. This is perhaps the most poetic twist of all, that the largest structures in the universe, the galaxies, the filaments, the clusters millions of light-years across, were seeded by the tiniest quantum fluctuations imaginable. In the early quantum sea, energy flickered and danced, appearing and disappearing as all quantum fields do. These minuscule differences in density were stretched across cosmic scales by inflation. Regions slightly denser than others pulled in more matter under gravity, eventually collapsing into stars, galaxies, and clusters. George Smoot, who mapped these primordial ripples, famously said, "If you're religious, it's like looking at the face of God." His point was not theological, but emotional. For in those tiny ripples lie the seeds of every world, every star, and eventually every living being. As we consider this chain of events, there's something deeply humbling about it. Everything we know, everything we are, arose from fluctuations far smaller than an atom. A quantum jitter stretched to cosmic size. That thought alone shifts the human perspective, reminding us that structure grows from chaos, and order can be born from uncertainty. In a way, inflation mirrors our own lives. We too begin with tiny choices, small turns, fleeting thoughts. And over time, those subtle fluctuations define the shape of our existence. Reflecting on inflation also teaches us a practical lesson about humility. We spend so much energy clinging to certainties, insisting that reality must conform to our intuition. Yet the early universe cared nothing for human logic. It evolved by laws deeper than instinct. The cosmos is not obligated to make sense to us. It simply is. And our task as scientists, dreamers, and curious minds is to listen carefully and patiently. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." Inflation is a reminder that even the wildest ideas can bring coherence to incomprehensible beginnings. When you look at the night sky, each star seems calm and eternal. Yet behind that quiet shine lies a history of impossible violence, an expansion faster than imagination, a smoothing of chaos. The galaxies we admire, the planets we explore, the atoms in our blood, all trace their roots back to those quantum ripples. Inflation is not merely a theory about the early universe. It is a story about how structure rises from emptiness, how order crystallizes from randomness, and how the universe, despite beginning in frantic uncertainty, found a way to grow into something astonishingly coherent. My own view is that inflation is one of the rare ideas that bridges the poetic and the scientific. It shows us how the universe could be sculpted by both chaos and symmetry, how randomness can be the seed of beauty. It reminds us that even the grandest structures begin as whispers. And perhaps that is a lesson worth carrying into our everyday lives. That from small beginnings, great worlds can emerge. In the end, inflation does more than explain the cosmos. It reveals a universe driven by tension between smoothness and fluctuation, between calm and storm. And in that balance, we find the blueprint not only of galaxies, but of existence itself. In recent years, our understanding of the cosmos has expanded into a realm once reserved only for myth and imagination. Physicists now speak not merely of a universe, but of a vast cosmic foam, an infinite sea in which our universe may be just a single shimmering bubble. The idea is at once humbling and exhilarating, a reminder that even the grandest structures we can observe may be only fragments of an even greater reality. As the Nobel laureate Steven Weinberg once said, "The more the universe seems comprehensible, the more it also seems pointless." Yet it is precisely in this apparent pointlessness that humanity discovers deeper meaning, because curiosity is the flame that turns the cold vacuum of space into a story worth telling. When we ask whether our cosmos is a bubble among countless others, we're entering the heart of modern cosmology, shaped by the Hubble expansion theory, inflationary physics, and a mysterious growth of spacetime itself. If our universe is expanding everywhere at once, and if that expansion has been fueled by a primordial burst of inflation, then it becomes natural to imagine that many such bursts occurred, each giving rise to a separate cosmic bubble. Alan Guth, the father of inflation, once remarked, "Inflation is not something that ends everywhere at once," suggesting that inflation may continue eternally, blooming new universes like sparks from a cosmic fire. Inside each bubble, the laws of physics could congeal differently, like frost patterns forming unique shapes on a window pane. Some universes might have stronger gravity, causing stars to collapse instantly into black holes. Others might have weaker electromagnetic forces, preventing atoms from forming at all. A few might contain dimensions curled into unknowable geometries, where what we call matter might not exist in any recognizable form. The physicist André Linde, a pioneer of chaotic inflation, beautifully summarized this by saying, "The universe is not just the universe. It's a multiverse where different parts are governed by different laws." And so arises a profound question. Is our universe fine-tuned, delicately balanced in its physical constants, as if crafted to allow life? The numbers that govern reality are astonishingly precise. The strength of gravity, the charge of the electron, the rate of cosmic expansion. Change any of them by a fraction of a fraction, and stars would not burn, planets would not form, and consciousness would never arise to ask these questions. Even the late Stephen Hawking noted, "The laws of science, as we know them today, contain many fundamental numbers, whose values seem to be very finely adjusted." One explanation is that our universe is special, rare, a miraculous oasis in a vast desert of sterile bubbles. Another explanation is more subtle, more elegant, more humbling. Life exists here not because the universe was crafted for life, but because in a multiverse containing countless universes, life can only arise in those with the right conditions. And so naturally, observers will always find themselves in universes that appear fine-tuned. Yet, for all our theories, for all our instruments, for all the photons we have collected across billions of light years, we remain bound by a fundamental boundary: the observable universe. A sphere about 93 billion light-years across, defined not by walls, but by time. There is no telescope powerful enough, no equation perfect enough, to let us see beyond the cosmic horizon. What lies beyond that shimmering limit, that veil of distance and time? Are there galaxies rushing away faster than light, forever unreachable? Are there entire universes budding just beyond our perceptual shoreline, expanding into realms we will never witness? Or is the boundary simply the edge of our understanding, not the edge of reality? The astrophysicist Sean Carroll once said, "The universe is not only stranger than we imagine, it is stranger than we can imagine." And perhaps this is the quiet truth behind our questions, that asking them is as important as answering them. Every inquiry is a step out of darkness. Every theory is a lantern we raise against the infinite. From a personal viewpoint, The multiverse does not diminish our significance. It expands it. If reality contains endless bubbles, then each cosmos is a verse in a greater cosmic poem. And our universe happens to be one where consciousness learned to read the lines. The miracle is not that we are small, but that we can see so far, think so deeply, and question the very fabric of existence. The lesson we draw is simple, yet profound. Our observable universe is limited, but our curiosity is not. The horizon may define what we can see, but it does not define what we can imagine. And imagination, paired with scientific rigor, is the vessel that carries us into the unknown. Perhaps one day, new physics will pierce the horizon, revealing what lies beyond, whether it is darkness or countless universes. Or perhaps the multiverse will remain forever speculative, a beautiful possibility dancing just beyond reach. Either way, the pursuit itself enriches us. For we are a species defined not by certainty, but by the unstoppable desire to understand. In this vast cosmos, in this fragile bubble of space-time we call home, our questions are constellations, lighting the darkness between what we know and what we dream. And as long as we continue asking them, we remain connected to the universe in the most human way possible. Through wonder, through curiosity, through the quiet courage to imagine what lies beyond the horizon. From the moment humanity first raised its eyes to the night sky, the question of the universe's shape has followed us like a quiet shadow. Scientists have long wondered whether the cosmos is a closed, curved realm destined to fold back upon itself, an open saddle expanding into endless possibility, or a perfectly flat canvas stretching outward in silent equilibrium. As Albert Einstein once reflected, the most incomprehensible thing about the universe is that it is comprehensible. And in this spirit we attempt to read the subtle geometry hidden within the cosmic web. To understand whether the universe is closed, open, or flat, we must first confront the idea of critical density. This is the delicate threshold where gravity's inward pull and the outward thrust of expansion are balanced so finely that the fabric of space neither collapses nor curves back. The physicist Stephen Hawking often emphasized this cosmic knife edge, noting that if the density of the universe were a little greater, space would eventually collapse, but if it were less, it would expand too quickly for galaxies and stars to form. The critical density is therefore not just a number. It is the silent architect of the universe's fate. When astronomers measured this density through the cosmic microwave background and the clustering of galaxies, something astonishing emerged. The universe appears remarkably flat, so flat that its curvature is immeasurable on the largest scales. This finding echoes the words of cosmologist Max Tegmark. The universe seems fine-tuned to a precision that is simply mind-blowing. A perfectly flat universe means parallel lines never meet. Space does not bend back like a sphere, nor flare out like a saddle. Instead, it behaves like an infinite plane, where geometry follows the comfortable rules we learned in childhood. But why should the universe be so perfectly balanced, so exquisitely tuned? Inflation theory offers a poetic explanation. During the earliest fraction of a second after the Big Bang, space is believed to have stretched faster than the speed of light. In doing so, it smoothed out any initial curvature like a sheet being pulled tightly across a frame, leaving behind a cosmos that appears flat, even if its true nature may be subtly curved on unattainable scales. Alan Guth, the father of inflation, once remarked that inflation explains why the world is the way it is. And indeed, it grants us a universe startling in its precision. Yet the shape of the universe is closely intertwined with its destiny. And as we follow the thread of geometry into the far future, we encounter two haunting possibilities. If the universe were closed, its gravity would one day overwhelm the expansion, pulling everything back inward. Stars, galaxies, and even space itself collapsing into a fiery finale known as the Big Crunch. Carl Sagan describes such cosmic cycles as the universe breathing in and out across eternity, a poetic vision of endless rebirth. But this dream of a cyclical cosmos fades under the cold light of modern measurements. Dark energy, the mysterious force accelerating the universe's expansion, has rewritten our cosmic fate. Instead of slowing down, galaxies drift apart faster with every passing epoch. Space itself seems restless, stretching not merely outward, but away from its own past. This acceleration points not toward a crunch, but toward a freeze. The Big Freeze is the most likely ending for our universe. A slow, quiet fading rather than a dramatic collapse. As dark energy continues its relentless push, galaxies will disappear beyond our cosmic horizon, their light stretched into invisibility. Over trillions of years, stars will exhaust their fuel, planets will drift through cold shadow, and the universe will settle into a thin, quiet sea of cooling atoms. Physicist Lawrence Krauss once said, "In the far future, not only will life as we know it be impossible, but even the memory of the universe we see today will fade into darkness. A universe that ends in silence, not fire." And yet, there is something profoundly human in contemplating this distant future. Something tender, something reflective. For even as we consider cold destinies and vanishing galaxies, we cannot escape the quiet beauty of the present moment. The fact that the universe is flat, that it balances on the edge of critical density, that it allows galaxies, stars, and life to form, feels less like an accident and more like an invitation, an opening into wonder. My own view is that the lesson hidden within this cosmic architecture is not about endings, but about perspective. When we realize that the universe had to be balanced almost impossibly well for us to exist, our worries shrink, not into insignificance, but into alignment. We belong to a cosmos that is delicate, precise, and breathtakingly grand. The Big Freeze reminds us that everything is temporary, and therefore precious. The flat geometry reminds us that balance is powerful. And the search for how big is the universe becomes less a scientific question and more a meditation on our place within it. In the end, the universe's shape is more than a scientific curiosity. It is a story about the impossible harmony that makes existence possible. A reminder that though the cosmos may one day grow cold, our curiosity burns brightly now, urging us to keep exploring. For as long as there are minds to wonder, the universe will never be entirely dark. The deeper we peer into the universe, the stranger its story becomes. For most of the 20th century, scientists believed that cosmic expansion should slow down under the weight of gravity, a natural braking force acting on all matter. Yet when astronomers studied distant supernovae at the end of the 1990 seconds, they found something utterly unexpected. The universe was not slowing. It was accelerating. Stephen Hawking once remarked that the greatest enemy of knowledge is not ignorance, but the illusion of knowledge. And this discovery proved just how incomplete our understanding truly was. Something was pushing the fabric of space itself outward with increasing speed. Something invisible, subtle, and immeasurable except through its effects. We now call this mysterious driver dark energy, though the name is more an admission of confusion than an explanation. The renowned physicist Michael Turner described dark energy as the most profound mystery in all of science, a sentence that captures the mixture of awe and humility it inspires. Unlike ordinary matter or radiation, dark energy does not dilute as space expands. Instead, it remains constant or perhaps even strengthens, meaning that the more space is created, the more this invisible pressure accelerates that creation. It is a cosmic feedback loop, subtle at first, then overwhelming. Einstein once introduced a term into his field equations: the cosmological constant, a stabilizing force he later called his greatest blunder. Yet modern observations suggest that this constant may have been an accidental glimpse of dark energy all along. As space continues to accelerate, the consequences for the universe are profound. Galaxies that are now faint smudges at the edge of our telescopes will drift away faster than the speed at which their light can reach us. This does not violate relativity, because it is space itself that stretches, not the galaxies racing through it. One day, their light will no longer arrive, and these island universes will slip beyond a horizon of eternal silence. Cosmologist Lawrence Krauss once said, "Someday, all we will see is our own galaxy, and people will think the universe is small." That is the fate awaiting our distant descendants. A sky emptied not by darkness, but by expansion. And when those future astronomers look outward, they will find no trace of the Big Bang. The cosmic microwave background, our oldest postcard from the early universe, will be stretched by expansion until its wavelengths become impossibly long, too faint to detect by any conceivable instrument. The galaxies that now help us measure expansion will be gone, the large-scale structure smoothed out. In a universe ruled by dark energy, history itself evaporates, leaving behind a lonely cosmic island with no memory of its origin. Nobel laureate Adam Rees reflected on this sobering truth. We are living at a privileged moment, the only moment when the universe is observable in its full glory. As we consider these revelations, something deeper unfolds. Not just an explanation of cosmic acceleration, but a reminder of how fragile our understanding is. Every generation believes it stands near the summit of knowledge, yet the universe reveals new wonders with the patience of eternity. My own perspective is shaped by this tension between certainty and humility. a recognition that the cosmos is not obligated to be simple, and that our curiosity is the only light guiding us into its depths. Dark energy, whatever it truly is, teaches us a lesson of profound importance: that the most powerful forces shaping existence may be the ones we cannot see. The universe expands, accelerates, erases its own past, and in doing so invites us to consider our place within it. We are brief sparks on a drifting world, trying to understand a cosmos that is already slipping away from us. Yet, this fleeting moment of clarity, this era where the evidence still lingers in the sky, is a gift. A reminder to study, to question, and above all, to wonder. The lesson we draw is simple yet transformative. Nothing about the universe is guaranteed to remain knowable. Knowledge itself has a cosmic window, one that opens only briefly. We stand in that window now, looking out across a horizon that future minds will never see. And perhaps that is the true meaning of dark energy. Not merely an accelerating expansion, but a reminder that our understanding must accelerate as well. That curiosity must move faster than the fading of the universe. And that wonder is the one force capable of outrunning the dark. Since the earliest days of astronomy, humanity has asked where the universe ends. Yet modern cosmology offers a quiet but astonishing correction. The true edge of the universe is not a distant wall at the far end of space. It is a moment in time. The farther we look into the night sky, the more ancient the light becomes. Until at last, every telescope, every detector, every dreaming scientist reaches the same shimmering boundary, the point where the universe first became transparent. That luminous veil is not a spatial frontier. It is a temporal one. As Stephen Hawking once said, the past, like the edge of the earth once imagined, is not a physical cliff, but a boundary of understanding. To grasp why the universe's edge is time itself, we must first accept a truth that feels almost poetic. Every time we look outward, we are also looking backward. Light has a speed, a limit woven into the fabric of reality. So the farther its journey, the older its story. When we observe a galaxy a billion light years away, we see it as it was a billion years ago. When we stare past the great spirals toward the faint primordial haze, we approach the universe as it existed just a heartbeat after its birth. And eventually, whether we gaze with Hubble, Webb, or any future instrument, we reach a limit. A soft, glowing sphere of microwave light that surrounds us on all sides. This is the cosmic microwave background, the first light ever released. Before that moment, the universe was too hot, too dense, too chaotic for photons to travel freely. There was no light to see, no space in the visual sense, only a seething fog of plasma. Here, we encounter the profound meaning behind the idea that the Big Bang is the ultimate edge. Not because space stops there, but because time itself begins there. Asking what lies beyond the Big Bang is like asking, what lies north of the North Pole? A question that folds in on itself. Time is not a hallway stretching into eternity behind us. It is a river with a source. As Carl Sagan once reflected, the cosmos is within us, but it also has a beginning beyond which memory, physics, and language cannot travel. The Big Bang is not a blast in space, but the moment space and time came into being. To go before, it would mean stepping outside time itself, a concept our minds are not built to hold. This leads naturally to the next question. Why can we never travel to the edge of the universe? The answer rests not in our engines or rockets, but in the nature of spacetime. The universe does not expand into something. It is the expansion. Every region of space is moving away from every other region as the fabric stretches. Like patterns painted onto an inflating balloon. If you attempt to reach the edge, you are not moving toward a wall. You are traveling into the past. But even if you accelerate forever, you cannot outrun time. You cannot reach the moment before moments existed. The edge is everywhere around us, yet always unreachable. Alan Guth, the father of cosmic inflation, once described the early universe as a spark of existence stretched beyond comprehension in an instant. That same stretching is the reason we cannot outrun the expansion. The more distant a galaxy, the faster the space between us grows. Some galaxies recede faster than light, not because they break cosmic speed limits, but because the road beneath them lengthens faster than they can walk. Even light itself cannot catch up. To journey to the edge would require crossing regions where space-time carries everything away from us faster than any traveler could advance. And so we arrive at the last and most delicate question. Why is it perhaps meaningless to ask what happened after or before the Big Bang? Time, as Einstein taught, is not separate from space. It is part of the geometry of the universe. Without space-time, before has no meaning. Without matter, after has no anchor. Sean Carroll phrases it beautifully. The universe is not in time. Time is in the universe. The moment of the Big Bang is not a doorway we can peer behind, but the first page of the cosmic story. Asking what came before it is not wrong. It is simply outside the grammar of reality. Yet within these limits, something unexpectedly human emerges. The edge of the universe, though unreachable, reminds us of the boundaries of our own knowledge. And boundaries are beautiful. They invite us to lean forward, to wonder, to imagine. My own view, shaped by years of listening to astronomers and watching the sky through a lens, is that the edge is not a limit, but an invitation. It teaches humility, reminding us that understanding does not end with a final answer, but continues as long as we keep asking. It teaches gratitude, that in a universe so vast, so ancient, so unreachable, we are still able to glimpse the first light ever released. And it teaches wonder, the kind that makes us step outside on a quiet night, look up, and feel both small and infinite at once. In truth, the edge of the universe is not a destination. It is a reflection. It shows us how far light can travel, how far curiosity can reach, how far the human mind is willing to roam despite its fragile body. And if there is a lesson in all of this, it is that the mystery at the heart of the cosmos is not meant to frustrate us, but to accompany us. As long as we keep asking, the universe keeps opening. As long as we keep wondering, the first light keeps glowing. And as long as we keep listening, the edge of time continues whispering across the dark. The Big Bang is the nearest we will ever come to touching the origin of everything. Not because it hides from us, but because it is stitched into the fabric of what we are. Every atom in our bodies, every breath, every heartbeat traces its existence back to that moment. And though we may never reach the edge, we carry its echoes within us. In that sense, the edge of the universe is not distant at all. It is intimately close. It is the past written into our bones, the beginning folded into every cell. And perhaps that is the most meaningful truth of all. The universe's first moment is not out there. It is here, living through us. In the vast silence between galaxies, in the thin golden thread of consciousness that flickers within each of us, a question rises that feels both ancient and intimate. Why can a creature so small understand a universe so immense? Stephen Hawking once said that human beings are just a chemical scum on a moderate-sized planet. Yet somehow we can comprehend the laws that govern the stars. This paradox is not a flaw. It is the story of our species. We stand on a tiny world suspended in a gulf 46 billion light-years wide. Yet our minds stretch far beyond the horizon of our senses. Carl Sagan called us star stuff, contemplating the stars, a poetic truth that captures something profound. The universe is not only the stage on which life appears, it is the source of the very atoms that allow us to think. When we ask why humans can understand the universe, we are really asking why the universe evolved a fragment of itself capable of reflection. Brian Cox once remarked that we are the cosmos made conscious. And this idea resonates because it suggests that our curiosity is not accidental. It is the echo of cosmic processes unfolding through biology. Our intelligence arose from survival. Yet survival alone cannot explain why we can imagine dimensions unseen, why we can build telescopes that capture photons older than the Earth, why mathematics born from human abstraction so precisely maps the behavior of distant galaxies. Eugene Wigner called this the unreasonable effectiveness of mathematics, a mystery that hints that our thoughts mirror something deeply embedded in the structure of reality. Curiosity, the engine of science, is perhaps the most miraculous trait we possess. Animals explore for food, safety, or mating. But humans explore for meaning. We ask questions even when there is no reward, when the answers take centuries to uncover, when the pursuit requires building machines the size of cities just to observe a single particle. This kind of curiosity is not utilitarian. It is existential. Richard Feynman once said that he was happy not to know everything, because the pleasure is in discovering how things work. That playful hunger for understanding is the flame that carried us from cave paintings to gravitational wave observatories. It lifts us from the dust, giving us the audacity to imagine what lies beyond the observable universe. And yet, the observable universe is more than a physical boundary. It is a metaphor for our intellectual horizon, a shimmering edge where knowledge fades into mystery. What we know forms a luminous sphere around us, but what we do not know stretches outward infinitely, expanding each time a discovery pushes the boundary forward. Just as ancient light can only travel so far, our ideas too have a limit. For every breakthrough, 1,000 new questions awaken. The more we understand, the more we realize how much remains hidden. This is not discouraging. It is deeply human. Our curiosity does not shrink in the face of mystery. It grows. As Neil deGrasse Tyson said, "The universe is under no obligation to make sense to you." And yet, we persist, driven by a quiet faith that meaning exists even if it hides behind cosmic horizons. This persistence is our greatest strength, because the boundary of knowledge is not a wall. It is an invitation. The truth is that our ability to comprehend the universe may come from the universe itself. The laws of physics shaped the stars. The stars created the elements. The elements formed life. And life produced consciousness, tracing a single unbroken thread from the birth of atoms to the birth of thought. In this way, understanding the universe is the universe remembering its own story. And if this is true, then curiosity is not only a human trait, it is a cosmic impulse, a tendency of reality to question itself, to evolve, to seek deeper order within apparent chaos. That is why every new generation asks the same questions in new ways. Why we continue to push past the limits of our senses. Why we feel a strange longing when we look at the night sky. My personal belief is that our smallness is the very reason we strive for understanding. Small creatures must look outward, must imagine, must build meaning to survive. In our fragility we found wonder, and in wonder we found purpose. The universe gave us almost nothing in terms of size or strength, but it gave us a mind capable of reflection, empathy, and imagination. The lesson we can draw from this is simple and humbling. Knowledge is not a destination. It is a journey. The observable universe may have an edge, but our curiosity does not. Every time we expand the horizon of what we understand, we expand the universe within ourselves. And this inner universe, rich and boundless, may be the most important one we will ever explore. So when we ask why humans can understand the cosmos, the answer may be beautifully simple. Because the cosmos wanted to be understood, and it chose us. Fragile, curious, luminous beings, to carry its story forward. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. A sentence that feels almost prophetic when we explore how curved spacetime replaced the ancient idea of gravity as a simple pull. In the classical world imagined by Newton, the universe was a grand clockwork where every object tugged on every other through an invisible force. Newton himself admitted that he did not know how this action at a distance could occur. But the mathematics worked so magnificently that the mystery was tolerated. For centuries, this view shaped our instincts about motion, weight, and the architecture of the heavens. Yet even Newton's brilliance could not explain every subtle wobble in the sky, especially Mercury's stubborn orbit. It would take a mind willing to reshape space and time themselves to reveal a deeper truth. Einstein's general relativity arrived not as an attack on Newton, but as a quiet revolution, a reweaving of the cosmic fabric. In his vision, gravity was not a force, but the curvature of space-time. John Wheeler later distilled it into a line of poetic precision. Matter tells space-time how to curve, and space-time tells matter how to move. Suddenly, the planets were no longer being pulled. They were falling freely through a bent geometry sculpted by the sun's mass. This idea felt strange to our Euclidean intuition, yet its predictions matched nature with exquisite accuracy. Light bending during a solar eclipse, time slowing in strong gravity, the precession of Mercury. All fell beautifully into place. Still, gravity is not the only language through which the universe reveals itself. To measure its scale, shape, and destiny, humanity needed a ruler capable of stretching across the stars. That ruler came from the quiet work of Henrietta Swan Leavitt, a woman who transformed astronomy while working in a time when her contributions were undervalued. As she studied Cepheid variable stars, Leavitt discovered a simple, elegant relationship between their brightness and their pulsation period. The brighter they are, the slower they beat. This became the first reliable cosmic yardstick, allowing astronomers to calculate distances not by guesswork but by the star's own heartbeat. With Leavitt's law in hand, Edwin Hubble pointed the world's largest telescope toward the Andromeda Nebula and saw something astonishing. The Cepheid he measured was far too faint to lie within the Milky Way, revealing that Andromeda was not a cloud but an entire galaxy. The universe suddenly ballooned from one island of stars to countless archipelagos scattered across the cosmic ocean. But Hubble was not done. When he plotted the distances of galaxies against their redshifts, he found a straight line. The farther a galaxy is, the faster it recedes. The universe is expanding, he concluded, a sentence that rewrote the nature of reality. Einstein reportedly called his earlier attempt to force a static universe his greatest blunder. The cosmos was not still, but moving, stretching, evolving. Redshift, much like the Doppler shift in sound, became the universal signpost for cosmic motion. When a galaxy moves away, its light stretches, its wavelength lengthens, and the glow drifts toward red. This was not merely movement through space, but the expansion of space itself, a concept that defies the simplicity of everyday experience yet matches every observation we hold. And if the universe is expanding, there must have been a time when it was impossibly small, impossibly hot, impossibly young. The earliest fossil of that era is the cosmic, microwave background, the afterglow released when the universe cooled enough for electrons and protons to form atoms. Before that moment, light could not travel freely, trapped in a fog of scattering particles. When the fog lifted, photons streamed outward, carrying the imprint of the infant cosmos across billions of years. It is the oldest light we can see, cosmologist George Smoot described. Like looking at the face of God. The CMB is astonishingly uniform, yet peppered with tiny fluctuations that became the seeds of galaxies. These ripples, amplified by gravity and cosmic expansion, grew into the vast cosmic web we inhabit. And in this delicate interplay between smoothness and structure, we can almost hear the early universe exhale. All of this leads us to one of the most subtle questions in cosmology, a question that sometimes feels philosophical at heart. Is space expanding, or are galaxies simply moving through it? General relativity teaches that expansion is the stretching of the metric itself, not objects flying outward from a central explosion. As astrophysicist Sean Carroll once said, "Space expands not because galaxies push against it, but because expansion is what empty space naturally does." In this way, the universe behaves less like an explosion and more like rising dough. Galaxies carried apart as the fabric between them grows. Light traveling across this stretching stage becomes redder, older, thinner, until some galaxies recede so quickly that their light will never reach us. As I reflect on these ideas, I'm struck by a quiet truth. Each discovery emerged not from certainty but from curiosity, from the willingness to question our inherited intuition. Newton looked at falling apples and imagined forces, connecting worlds. Einstein looked at falling elevators and imagined space bending. Leavitt looked at flickering stars and imagined a universal rhythm. Hubble looked at faint smudges and imagined an expanding sky. The lesson hidden beneath these breakthroughs is simple. The universe rewards those who dare to ask better questions. We live in a cosmos shaped by mysteries yet illuminated by human insight. And every redshifted photon, every curved line of spacetime, every rhythmic pulse of a Cepheid is an invitation to understand our place in it. The universe expands, and so must our imagination. In the end, perhaps the most profound thought comes from Carl Sagan. We are a way for the cosmos to know itself. Through these discoveries, through these questions, we are teaching the universe its own story. And in that act, we give meaning to the light that has traveled so far to reach us.